Our last speaker today is Abdesselam, who will talk about correlation inequalities.
Thank you, Martin. Thank you to the organizers for the kind invitation and the opportunity to give this talk. So it's about correlation inequalities. Mostly try to present a conjecture, and then later I'll show you also some partial results in that direction. So this is part of this is joint work with two former postdocs at the University of Virginia, Gennady Uraltsev, who's now at the University of Arkansas, and Joe Webster, who's at Grenoble College. I have to warn you, my talk really starts at slide number 10, so I have to buzz through the first few slides, which are basically reviewing things which I think the audience knows very well, especially after the talks that we had. So it's going to be about what's a spin system, what's a lattice gauge theory, is that I think most of you know. All right, just to give some context and essentially present notation. Spin systems. So typically, we want to study random functions from a lattice, like ZD, into some target space T, the space where each spin takes its values. And I want to present this in kind of in a general setting. So, of course, the T then is going to become, for example, the sphere if we're talking about the ON model, but okay, let's take some general space T. All right, so we want to study some probability measures. I'm not going to put the magnetic field. My only parameter is going to be beta, the temperature, inverse temperature. And so I'm going to be looking at, the family of probability measures nu sub beta on the probability space, which is basically a product of so the space of functions from ZD into T, so omega here. So a spin configuration is an element of omega, is basically an assignment of a spin sigma x for every site x. Good. So these measures are typically of the form, the following form. So we start from so we suppose that our space T comes with a natural measure. So for the sphere, think the uniform measure on the sphere. So there's also a group which acts, and so you want this measure to be invariant by that group. So that's the single spin measure mu SS, and then you build the free measure on omega by taking the product. And that's also the beta equals 0 particular case, mu sub 0. And then we modify this by Gibbs weight exponential minus beta h of sigma, where h of sigma is some energy. Oops, I'm going the wrong way. All right. And so you typically, that's a little bit heuristic because the summation is over the entire infinite lattice, but essentially you want something of this form. So for two-body interactions between the spin at site x and the site y, you want to plug them into some function phi, and real valued function, and then you put a coupling jxy, and you want to sum over all points x and y in ZE. Okay, of course, just so you have a concrete example, the most famous example of such spin models is the Ising model, which corresponds to the case where T is just the set 1 and minus 1. The single spin is just 1/2 for each of these two values, and this function phi will just take the product. Okay, so that gives you the Ising model. Now, what about these couplings gxy? So you see that here I didn't put the condition that x and y are nearest neighbors, so you can work more generally. I mean, you can define this on any graph, not just ZD. But the most studied is, of course, the short-range Ising model. And so this one is just an indicator function. So this is the indicator function of the condition that x and y are nearest neighbors. That gives you the most studied example, the short-range Ising model. But very interesting also are the so-called long-range Ising models, where you coupled site x and y with a weight which has this behavior, and you want the power to be bigger than the dimension. You want to be able to sum over y if you fix x, for example. Okay. All right. So good. And of course, one is mostly interested in understanding phase transitions. So, just to remind you, of course, for short-range Ising, in dimension at least 2, we know there is a critical beta, so for high temperature, so below, if you look at the 2-point function, at long distance it goes to 0, whereas at low temperature it doesn't go to 0. Notice that since I didn't introduce a magnetic field at all, so I have to have some witness of a phase transition which doesn't involve a magnetic field, so this is the long-range order versus not way of characterizing this phase transition. Good, but all right, so the easing model is a particular case of a more general class of models, which is the OM model. So in that case, the target T is the sphere in Rn. So n equal 1, that gives you easing. In that case, you want also to take the single spin measure to be the uniform measure. And instead of the product sigma 1 times sigma 2 for your function phi, which sits in the Hamiltonian, you take the dot product. Okay, so that's another more general class of examples. And okay, so we heard on Monday about this conjecture by Polyakov that in 2 dimensions and for n at least 3, that for any beta we expect that there should be exponential decay for arbitrary temperature. But of course this is extremely hard, and it's kind of a much simpler version of the mass gap for Yang-Mills in 4 dimensions. It's a similar flavor and it's even harder. Okay, and of course one of the major difficulties here is that the underlying group is non-Abelian when n is at least 3, whereas for n equal 1, easing, n equal 2, the xy or rotator model, a lot more is known. Okay. All right, so even faster review of lattice gauge theory. I might have to be really careful with time. Good. All right, so lattice gauge theory is a similar setup, but so you again have a lattice ZD, but the variables, instead of sitting at the sides, they will be sitting on the edges. Okay, so for each side x, so EI is just a canonical basis vector, so essentially it tells you the so x plus EI is an edge in the ith direction. So here we put a random variable u, which is in a compact Lie group, G, and we want to understand some probability measures depending on the parameter beta for these configurations. So basically this collection of random variables which sit on the group valued random variables which sit on the edges of this lattice. And of course, if you reverse the orientation of the edge, by definition, you just take the inverse of that group element. Good. So the setup is the same. It's a Gibbs weight. We start from all the variables being independent and with the distributed according to Haar measure. And then we perturb with exponential minus beta h. So now h is given by this type of formula. Instead of summing over 2 points, we sum over 4. And we have a function phi, which depends on the edge x1, x2, x2, x3, x3, x4, x4, x1, and a coupling function here. And so the analog of the short-range easing now, where the j was just an indicator function, which tells you that how the points have to sit relative to each other. Now this j is the indicator function that x1, x2, x3, x4 form what is called a plaquette, which is basically something like this, x1, and then you turn to x2, x3, x4. Okay, so this, that means that, okay, you can find 2 directions, I different from j, such that x2 is x1 plus, you move in the ith direction, then x3 if you move again in the jth direction, and then you come back. All right, and so what about the function phi? Function phi, so A, B, C, D are 4 group elements. So by definition, you take the product of these group elements, you stick them into a representation of that group, pi. You take the trace and you take the real part, okay? And you put that in your H, and that gives you some energy Okay, so then you're doing lattice gauge theory. Good. All right, so far I just talked heuristically because the sums were over the infinite lattice. So what we want to do is to be able to do the infinite volume limit rigorously. So typically you have to take a finite box lambda inside ZD and to have something well defined. When you define the Hamiltonian, you restrict the sum to lattice sites inside that box. This is in the spin model case, but you can also do this similar thing for lattice gauge theories. Good. So now instead of having nu sub beta, you have a new probability measure which depends on beta, but also lambda. Which is well defined, but now you want to take the limit where lambda goes to infinity, to the entire infinite lattice. And okay, so the configuration space is compact, so you can always take subsequences and get something, but you want something a bit more robust where you don't just have a bunch of limit points, you want to have unique limit points, or really weak conversions of as you take lambda goes to ZD, no matter what the sequence of boxes you take. But for that, you need some strong property, essentially correlation inequality. So you want to be able to prove that correlations converge, for example, because they increase. And so the main ingredient for that is monotonicity. So if you have so if you have an observable and you look at the derivative with respect to one of the couplings, x, y, if you do the computation, you get this kind of thing. So essentially you get a covariance of the observable that you were interested in, plus this phi which comes down from the exponential. And so to prove that your correlation increases as you turn the couplings, which is also another way of getting making the box bigger and bigger. You can realize that simply by turning on the couplings from 0 to some value. So you need for this what is called the GKS2 inequality, so this type of inequality. The GKS after Griffiths, Kelly, and Sherman, who proved this for the easy model. Later, G did it for XY, or the ON model with n equal 2. Okay, so the main big challenge is to prove this type of inequality for non-Abelian models. Now, for non-Abelian models, you have to be careful what kind of observables f and g you allow. They would have to be invariant observables. For example, inner products, or any kind of function that you take by taking products of inner products of spins, for example. Because if you just take some component of a spin, then it's clearly it's not going to be positively correlated, because on a sphere, if this component is big, then the other one has to be small. So, all right. Okay, so now the talk starts. That was just the context. Okay, so I want to study these GKS inequalities. I'm going to do it in a very abstract setting. Unfortunately, there's a little bit of shift of notation. So now x, what I call x, is what I called omega before, so it's the probability space. So you have some probability space and a bunch of random variables, so a bunch of functions, which I call observables, or basic observables. Okay, so suppose we have a finite number of them, O1, O2, O3, On. Good. All right, so if you have, and we start from a measure mu, so think about, for example, the independent, the product measure of a uniform measure on the sphere, for example. So we start from a reference measure mu. We have these functions, so these observables. Now we can build, so this is a very important notation for the rest of the talk. I mean, it's a bit more compact. So if I write OX power A, so what does that mean? A is a multi-index, so it's just a collection of exponents. And so that means I'm looking at the monomial built from these basic functions O1, O2, etc. Okay. Stop me if there's something unclear in the notation. Good. All right, so now I'm going to introduce a matrix, V, so M by N matrix. And so what's the purpose of this matrix is to store a bunch of these monomials. Okay, so O1, O, and these are the basic functions that I will use to build the rest. And now I have a matrix V, which is M by N. So each row of this matrix gives me a multi-index, and it will give me a certain monomial in these. Does that make sense? Right. So instead of having one multi-index A1, etc., AN, I'm going to have lots, and I'm going to store them as the rows of this matrix. Good. All right. Then I'm going to need also some. So these couplings. So it's a collection J of non-negative numbers, and so there is a coupling for each of these monomials, each of these rows. Good. Then what? Then, all right. So now, now I'm going to define a new measure. Actually, I'm going to do it in steps. So I want to. Should I jump right away? Okay, so I want to define this new measure on my space, mu sub j, which depends on these couplings. So I start from the say completely factorized simple measure mu that I had at the beginning, and this is a Gibbs weight. So what I have here is minus the Hamiltonian essentially, but in a more kind of a general setting. So how is that constructed? Well, basically. I'm going to take the monomial in the basic observables corresponding to the ith row of this matrix. Right? I'm going to put it there times its own coupling, j sub I, right, which is non-negative. Okay, and I put that in my exponential, and that gives me essentially my Gibbs weight. So let me go back one slide. So when I compute expectation with this new measure, it's going to be a ratio of, there's a normalization. It's going to be a ratio. It's going to be a ratio of things like this. So f is some function on my space x. Depends on j. Un here, it just means unnormalized. Okay, so because there is not 1 over z. Okay, so it's just the integral over the space x. So little x here, you should think of it as a spin configuration, for example. Of what? Of the observable f of x times this Gibbs weight. Okay, and of course if I take the unnormalized expectation of just a constant function equal to 1, that's my partition function z, and so to get the expectations of interest, I have to take this ratio. Is that right so far? Any question, especially about notation? Please ask. Okay. All right. So now I can introduce some definitions.
Yes. So would you remind what was n is the number of basic observables?
To give you kind of a running example, so
yeah.
Otherwise it's easy to get lost in my ever-changing notation. Where is the can I write here? Okay. So if you take lambda inside ZD, let me just forget that lambda is inside the lattice. It's just a finite set, and actually I'm just going to take 1, 2, 3 up to p, also denoted like this in combinatorics works. Okay, in that case, n is going to be p choose 2. And so what is O1, O2 up to On, which is p choose 2, is just all my inner products. So this is sigma 1 dot sigma 2, sigma 1 dot sigma 3, and here is going to be sigma p minus 1 dot sigma p. Does that make sense? So n is the total number of basic observables that I build the whole thing out of. And in that case, it's just the dot product of the spins for each pair. So that's n, and that's okay. Now I can put in my so you can, for example, look at what's called the generalized ON models, where in the exponential you don't just have two-body, just sigma I times dot sigma j. You can take products of things like that. with a positive weight and put the sum of those. So these are stored, all the monomials that I want to consider are stored in this matrix. Okay. Good. Okay, so for now it's just definitions. So such a system, so a probability space, so the basic data is my probability space X, the free measure mu, so the beta equals 0 measure if you want, and then some chosen collection of basic observables like these dot products. Okay. These are the basic input, and so I say that this system satisfies the first GKS inequality if we have that property. So no matter what monomial I build out of these basic observables, if I take the expectation with this funny measure, it should be non-negative. Okay. That one is not too complicated. So let's move on to the non-trivial one. So this is the GKS2 inequality. At this point, it's just a definition. We say that the system satisfies this property if blah, blah, blah. Okay, so the system satisfies this GKS2 collection of inequalities if for any matrix like this, for any value of the couplings, non-negative, and for any particular multi-indices A and B, I have this inequality, which means that the monomial O at the power A and O at the power B in the interacting measure, they are positively correlated. Does that make sense? It's a definition right now. Okay, so remember this is the normalized expectation, so you can of course clear denominators and then put things on the left-hand side. So in terms of the unnormalized, I got rid of the z, right? I multiplied by z squared everywhere. This becomes this inequality here. Right. Good. Now I'm going to do something a bit brutal, which is to expand this in terms of the couplings J. Right? If they're in the exponential, just expand. And here there should be a problem because it's compact, so it should be fine. Okay, so let's see if you follow this notation. That's essentially writing the result. Where is the yeah? Okay, so if you take one of these unnormalized expectations, where f now is some monomial O at the power A, brutally expand this exponential and pull out the sums and pull out the couplings J. What you will get in a kind of condensed notation is the following. Oops, is this thing here. Do you buy that? Okay, so, all right, so what is alpha? Alpha is a multi-index, but it's a multi-index with alpha 1 up to alpha n, right? So alpha I tells you how many times you pulled out the monomial for that, corresponding to that row from the exponential, right? Okay, so you get J alpha divided, okay, this is just the multi-index version of factorial. And, all right, when you look at the observable part, and this expectation here is with respect to the uncoupled, the beta equals 0 measure. So you have, that was the original f, which is O at the power A. But then what came down from the exponential, you can write it, so this is why I introduced this matrix. Here I take advantage of matrix algebra as an efficient system of notation. So basically, I have a multi-index alpha 1 dot alpha n, right? And I just take the product, and this gives me now a multi-index, which is alpha times v, just using the matrix product, which is a multi-index of size n corresponding to the list of basic observables, and that gives me a monomial in the basic observables, right? So is that right? So this is kind of a compact way of writing this brutal expansion. Good. So not hard, but it's important that this point is clear. Otherwise, after that, it's Okay, good. All right. All right, so where was I? Let me go back 1 second. So if you do, this requires quite a bit of practice. Okay, so if you do this expansion for all the terms that are present here, so this is just a GKS 2 inequality. So if you do this expansion for all these 4 unnormalized expectations, what you get is this mess. Okay, so what I did here is, okay, so you have an expansion. So the gamma here is just, okay, so you have, for this left factor, you have a sum over alpha. You have also a sum over beta for the other factor, same thing for these 2 things here. But then the power of the couplings is going to be the sum of what comes from here and here. So that means it's going to be this multi-index gamma, which is the sum of these 2 multi-indices. Good, and so what I did is to separate the couplings from the rest, right? So I have this series in terms of these couplings times these complicated combinatorial sums here, and I want this to be non-negative. All right, so of course a much stronger statement than saying that this whole thing is non-negative is that for every monomial in the couplings, this mess has to be non-negative. Does that make sense? Good. So remember so we're working with a ferromagnetic system. So these J's are by assumption non-negative. So of course one would be happy and would have the GKS2 inequality if one can prove that each of these sums is non-negative for every gamma, or essentially for every monomial in the couplings. Good. So that allows me to introduce a new definition. We're just doing definition. So I will say that, did I say, all right. So I will say that my system, probability space, free measure, collection of observables, satisfies the CGKS2, or C stands for coefficient-wise, so monomial by monomial in the couplings. If the coefficient of that monomial, which is this horrible mess, is non-negative. And in fact, many of you know how to prove GKS2 using Gennady. Essentially, this is how it's done. It's done by a reduction to this to expectation with respect to the free measure. The couplings play no role. Good. All right. And now something new, I think. So let me introduce a even stronger condition, which I will call the shifted coefficient-wise GKS2. All right, so again, it's a definition. X mu O satisfies this S, G, if no matter what this matrix V is, no matter what the multi-indices A, B, R, and gamma, this thing is non-negative. So what is the difference with the previous one? Is that I added the same monomial U to all the exponents. So that's why I call it a shifted version. Okay. So this, I think, hasn't really been considered before, and I'll explain, you'll see later why I need that.
Positive, you mean each term in the sum has to be positive, or just the sum? When you say positive, you mean each term in the sum has to be positive, or
no,
just the sum?
So this sum has to be positive, but this sum itself is a coefficient in a bigger sum. So saying that the previous sum had each term in the previous sum has to be non-negative means that each one of these sums is non-negative. Does that make sense? Okay, good. So I'll let you. All right. So this is a definition, and I think now I can give a conjecture. Fine. My conjecture is that. How am I doing for time? So the conjecture is that the following models should satisfy this stronger, shifted coefficient-wise GKS2 inequalities. So there is the RPN model. I'm not yet confident about the ON model. I'll explain the definition in a second. So to be more conservative, I'll just state it for the RPN-1. The CPN-1 model, but there is also a more general class of spin models where the T is a Grassmannian. You can even also do flag varieties. You can also take, so this is like lattice gauge theories, but it's turned into a spin model, so it's so-called the principal chiral model, where the spins live on the lattice sides, but they're valued in a group. That's also kind of a spin model. And then I conjectured that this should also be true for lattice gauge theories. And again, to be careful, I will take the adjoint representation, so the trace, the real part of the trace of the representation applied to the product of group elements. In that case, it just becomes the modulus squared of the trace of the product, when pi is the adjoint representation. And I put dot because I think this should be true in much wider generality, but this is work in progress to try to make this precise. Okay, any questions so far? So just to remind you, okay, so now to be more precise and kind of tying up with this example. Okay, so the ON model that corresponds to the case where X, the probability space, is basically a product of spheres S n minus 1 inside Rn. P, because here you can do this over any graph, so you can forget that you're in a lattice. So any finite set, indexing the sites is good enough. So for ON, the total, I mean, the basic observables are given by the dot products. So what is the Rpn-1 model? For those of you who might not be familiar, is basically the same thing, but instead of taking the dot products as your basic observables, you take the squares of the dot products. So essentially it means that you cannot see the difference between a spin and its negative. So it's not a model of kind of arrows pointing in some direction, it's more a model of lines without a direction. So it's used, for example, to study liquid crystals and things like that. So the Rpn-1 model. What is the CPN model? It's also a very important model studied in high energy physics and all that. In that case, so it's a complex version. So you look at Cn instead of Rn this time, and you look with the Hermitian inner product Z bar, which I like to do like in physics, antilinear on the left and linear on the right. Okay, so the standard Hermitian inner product, and so this defines a unit sphere of real dimension 2n minus 1. So you can take X to be, this is kind of a lifted version, so you can take X to be that. And then for your basic observables, so what I call the O1 up to O P choose 2, you take the Hermitian inner product between two spins, you take the modulus squared. You look at this collection over all pairs. So why is it called a CPN-1 model? So it's because if you multiply these vectors by a phase, you won't see it. It will be killed by this modulus squared. So really, this is not a model over a product of these spheres, but rather these spheres divided by a U1. So it's really the projective space where you spin the values. Good. All right. So okay. So before that was conjecture. Now, what about results? What did we prove about these things? Okay. So and by the way, so there is already this preprint that I'm still working on, but you can find already these results here on Archive, and there is also 2 papers in preparation with Gennady and Joe. All right, so what is the idea here? So let me go back, maybe. Okay, I showed you this monster. Oops. I showed you this monster inequality. If you can prove this for any of these systems for u equals 0, then you have GTS2, and then you're happy. Okay. So this is a bit more general with the u. Good. Now I'm going to make it even more complicated. How? By scaling all these monomials by the same number, and I'm going to look at the asymptotic when the number goes to infinity. Okay. So I will be looking at this. So it's the same inequality as before, but where the exponents have been boosted by multiplying by some lambda. Right? And so where we have results is that when you take lambda, actually not, you don't need to take lambda to infinity, you just need to take lambda big enough. Then these become true. That's the result. So at least, I mean, we have an infinite collection of inequalities here that one would have to prove to get the GKS2 type inequalities. And okay, managed to prove that these extremely complicated combinatorial inequalities are true, at least if lambda is large enough. So hopefully it's not complete nonsense.
Large enough depends on the size of the graph.
Yes, yeah. So this is actually so a very good question. So this is so the asymptotics is essentially this is like a semi-classical type of asymptotics because we're close to this. When you take lambda large, if you think spin model, that kind of forces the spins to be close to be aligned essentially. So it's a semi-classical regime, but we don't have any. We cannot do uniform control, uniform in the volume because this is basically like doing the Engel's problem, right? Being able to control lattice gauge theories or the one model for high beta. But it's different from beta because this is in terms of the free measure, but you have to do it for lots of combinatorial data, for lots of A's and B's and V's, etc. Good. All right, so what is this asymptotic?
And another question, the lambda large also depends on the A, B, U's and so on, or is it independent?
Yeah. So if you want the result that for lambda large enough, bigger than blah, the inequality holds, and in fact it's strict inequality, the lambda has to be larger than something that depends on everything. So, yeah. It depends on the number of sites and depends on A, B. Good. All right. So what is this asymptotic property? So if you look at let me maybe start with the CPN model. So you take a product of basic observables where you have the Hermitian inner products modulus squared. At some raised at some monomial a1, a2, an, but then you multiply everybody by lambda and you take lambda go to infinity. And this is expectation with respect to the free measure, beta equals 0 measure. What do you get? You get this. All right, so you have the gamma function at the power p minus 1. P is the number of lattice sites. Well, not very interesting, but okay. And then you have lambda at this power. So notice that this involves the number of lattice sites minus 1. And then times, this is essentially the real dimension. This is, so it's better to put over 2 and compensate with a 2. So maybe here. So here you have the real dimension of the sphere. Here there is a hidden 1/2 times 2 n minus 1, which is the dimension of the projective space as a real manifold. This is just to explain what the meaning of these exponents here. And the interesting part, which is where is the dependence in the original monomial, or if you want the multi-index of exponents A. It's all in this quantity here, so I write it k of A. Why? Because this is the famous Kirchhoff polynomial. Right, so in the case of a spin model, not lattice gauge theory, so what is this? So remember the A's, you have A1 up to A, P choose 2, so the A's are indexed by pairs of sites. And so the K of A is the sum over all spanning trees of product over the edges of the spanning tree of the A of that edge. Everyone has seen that? Okay, so this is the famous Kirchhoff polynomial, which appears in the so-called matrix tree theorem. And this is basically what comes out. At the power n minus 1. Good. So this is for the CP n minus 1 model. If you do the RP n minus 1 model, you get essentially this. So there is this kind of factor of 2. So here instead of n minus 1, you have n minus 1 over 2. So again, it has to do with the real dimension of the target space. Okay, good. So These are particular cases of much more general asymptotics where we looked at like target spaces, which are Grassmannians and the Carroll model, lattice gauge theories, and things like that. So all of these examples, instead of this Kirchhoff polynomial, when you do similar asymptotics, so this is work with Gennady and Joe, we get some function here at a negative power, which is an integer over 2. And so typically this function, instead of k of a, in general is something as a function of the components of the multi-index, a, now I will write it x, sorry, is what is called a stable determinantal polynomial. And the Kirchhoff polynomial by the matrix tree theorem is an example of that. So what is, in general, what is called a stable determinantal polynomial? Okay, so if you have n variables, x1, xn, a polynomial in these variables is called stable polynomial if it's the determinant of this kind of linear combination where the matrices a1 up to an are real symmetric. They're positive semi-definite, and when you add them all together, then you're strictly positive definite. Okay, so because of that, when you stick, so this allows you to define a function on a cone, basically the positive orthant, where all the x's are strictly positive, and it's non-zero, so this is called a stable determinantal polynomial because, okay, so there's lots of work about these kind of things. They have the property that, so the coefficients are real because the matrices are real, and this, okay, needs a little proof, but so this is non-vanishing if, for example, all the numbers have strictly positive imaginary form. That's the stable form. And this has been studied a lot, in particular by and Brandon. What time? How much?
10 minutes?
10 minutes?
12 minutes.
Okay. So the Kirchhoff polynomial k is an example of such a function p by the matrix tree theorem. And so what I proved in this archive paper is that and essentially these shifted coefficient-wise GKS2 type inequalities, they hold if you do just one little cheat. So remember that these complicated, I mean, okay, you won't remember the formula, but it's some horrible formula in terms of these expectations with respect to the free measure of some monomial in the basic observables, right? So which depend on the exponents a1 up to an. So the cheat is whatever you see one of these things, just replace by stick those a's into your polynomial p, like the Kirchhoff polynomial, and raised to a power which is minus an integer over 2. Remember, before the R was n minus 1 for the ON and the CPN model. Okay, so if you do this, okay, this is essentially a rewriting. Actually, it's a bit more general than the previous inequalities, so that's why it looks a little bit different. And it involves some signs here. Okay, maybe I'll skip the detailed explanation. And essentially, this is kind of more like Gennady, the general Gennady inequalities, rather than the coefficient-wise GKS inequalities. What we need in the previous setup is the case where there is only two epsilons which are negative. Okay, so right. So this is more general than replacing the true expectations by these polynomial evaluation at the negative power that we needed before. So this is more good. So, but again, so in the case where you take lambda big enough, then we can prove that these inequalities hold, and therefore this gives a little bit of evidence for some ferromagnetic behavior, even in models which are non-Abelian. Maybe I'll skip this theorem here. This is just a strengthening of the previous inequality, which gives you some strict inequality. By the way, maybe I can you can see why I need this shift Remember, the polynomial is defined in some orthant. So for things to be well behaved, in particular, since I take negative powers of p, I need p to be non-zero, so I have to be in the interior of this cone. And what you need for GKS is at the boundary. So the generalization essentially means, okay, you have this wider cone. If you can prove the inequalities in the cone, then maybe it should hold also in the boundary. Good, and this is the last slide. So I think I'll be able to finish on, maybe even earlier. I went a bit too fast. Okay, so what other results as far as, okay, should we believe that ON or all these non-Abelian models satisfy the GKS two inequalities? A simpler version where actually there is nothing here. So essentially it corresponds to the GKS at at beta equals 0. So I mean, if you want to prove GKS for the true model, you should at least work for beta equals 0. And actually, so for the ON model, I don't think this is well known, but this has been proven a long time ago by Baumgartner and Ira Herbst. So this is the beta equals 0 ON model, and it corresponds to putting u equals 0 here. So for u equals 0, this is true, it has been proved. Actually, this is not an archive, but I generalized, again with u equals 0, I generalized this proof, but where now n is not necessarily an integer. So you might say, well, what does that mean to integrate over a spin which in a sphere of dimension 3.5? Well, it makes sense. And actually, there is a canonical, a unique way to analytically continue, if you want, in the n. The correlations with respect to the invariant at the factorized measure. And for that definition of how you analytically continue, so for any n real, at least equal to 1, I was able to prove this for the ON as well as for the CPN model, but still for u equals 0. For u non-zero, I was able to prove this for any n real, at least 1, for the CPN with 3 lattice sites. That's all I can do for now. Okay, so that's basically it.